around 1911, Niels Bohr, completed his basic work on the hydrogen atom and by introducing the idea that electrons around atoms did not spin at all levels, but only at particular levels, and at those levels they gave off no radiation. And he developed what's called quantum levels, and that electrons could jump from one level to another, and when they came down they gave off energy. But these are what's now called the principal quantum numbers. The principal quantum number of an atom, in particular hydrogen. And they went from 1 to 7. Now, in about 1920-22, some things started to happen that changed this model, built upon this model is a better way of describing it. The first person that did some work on it was a guy by the name of Heisenberg. And Heisenberg, knowing the size of them, the incredibly small size of the electron and the speed of the electron, with some basic calculations, he came up with the position that it was impossible to know simultaneously the location and the speed or velocity of an electron. Speed times mass is momentum. But this principle then had all the scientists saying, we have to now start dealing with probability issues on the electron. We'll never find where it is exactly. Open the door, and very similar, at a very matter of a year's time period, a person from the Sorbonne University in Paris, by the name, his name was de Broglie. He was a doctoral student, and he came up with a proposal that really shook things up. That he said that the guy he admired, Einstein, came up with the equation that light could be a particle called a photon. All right, light could be a particle. Well, he reasoned that why couldn't a particle be light? And he came up with the equation that won a Nobel Prize. Incidentally, his doctoral committee had to send his work to Einstein to see that it made sense. But here is the issue. That's a wave. That is a wave of an electron. This is a particle of electron. They're both in the same equation. They're related by this famous equation. Electron can be a wave and a particle, which was proven several years after he proposed this. Well, these two ideas came together into some marvelous mathematics by a guy by the name of Schrödinger. Very complicated calculus, advanced calculus. Schrödinger's wave equations used this work, light as a wave and a particle, and came up with some mathematical solutions that redefined an atom from a probability model into something smaller spaces, and had particular energy levels and shape. And these things were called orbitals. Orbitals, not orbits, but orbitals. Okay? Now these orbitals, and we'll go back to this one up here. Remember, here the electrons jump from one level to another according to Bohr, but now the orbitals, and you could have one orbital at the first level according to the solutions. At the second level you had two types of orbitals. These were called the s orbitals. And then you had three orbitals, the same type of orbitals, called p orbitals. The second level. And at the third level you had s, p, and 5 of these d's. Now, these orbitals, in terms of hydrogen, were all at the same energy level. So if an electron jumped from one level to another, you got identical results to Niels Bohr. But where you started to get variations in results is when you went to multi-electron atoms. And now you had one here, and these two p orbitals were slightly higher energy than the s. And at the third level, you had S, P, and D. And D was higher than P, which was higher than S. So when electrons got in these atoms, you got a much more sophisticated view of the atom. These orbitals here would go in different directions, and they're called the third quantum number, the magnetic quantum number. This is the directional one. And the fourth one was developed separately. These were not Schrodinger's, the fourth one. And this was called the spin quantum number. And this was developed by Wolfgang Pauli. And Pauli proposed that in these electrons, if there's more than one electron, they have to spin in opposite direction to coexist, otherwise they'd fly apart. And these arrows indicated the spin, clockwise and counterclockwise. So orbitals could have 0, 1, or 2 electrons. And the second thing that Pauli ended up with saying, every atom and every electron will all have a different set of 4 quantum numbers. Okay, we will now go into electron configuration, and we'll stop right there.